Okay, so the last type of things that you could express in moles, or at least that we're going to talk about right now, is ionic compounds. So NaCl, sodium chloride, which is table salt. You can also have a mole of that, all right? In fact, this right here, I'm going to tell you in a second, is a mole of sodium chloride, all right? But the thing is that what is it? It's 6.02 times 10 to the 23rd of what, all right? And the thing is, whenever you have an ionic compound, such as sodium chloride, the reason you know it's ionic is because it's one blue element with one pink element. You say it's that many formula units of NaCl, all right? And what's the reason for that? Okay, the reason is that on the smallest level, sodium chloride, it's not made of molecules. There's no such thing as a molecule of sodium chloride, all right? What it means to be a molecule is that the things are covalently bonded to each other. Okay? All right, so we were talking a second ago about the term mole, all right? And what we were saying is that a mole just means that you have 6.02 times 10 to the 23rd of whatever you have, okay? And to kind of give you a feel for what that means in terms of chemistry here, let's see, try to get that on camera. What I've done is I've drawn two different molecules here. This guy right here is glucose, all right? This right here, that white powder in that beaker, is glucose, all right? Glucose is the sugar that your body burns. This right here is sucrose, all right? Sucrose is just normal table sugar, all right? This right here is just normal table sugar, all right? So one thing that's obvious about these two molecules is the size, all right? If you take a look at how big this guy is compared to this guy, obviously sucrose is a larger molecule, all right? If you were to take the formulas, this is C12H22O11. All right, do the same for glucose. It's C6H12O6. All right, sucrose is almost twice as big as a glucose molecule. All right, and so here's the analogy. In this beaker right here, I've got a dozen lentil beans. All right, in this vial right here, I've got a dozen kidney beans, all right? Obviously, an individual lentil bean is a lot smaller than an individual kidney bean. So if I were to hold one up next to the other, which one, if you were to blur your vision and say, what is there more of? All right, it looks like there's more kidney beans there. Not individual kidney beans, but like if you were to weigh, you know, this number of kidney beans and weigh this much lentil beans, which looks like it would weigh more? All right, obviously the kidney beans would weigh a lot more. The reason for that is obviously because each individual kidney bean weighs more than each individual lentil bean. All right, so if you have the same quantity of two differently sized particles, then it's going to be the one that that is larger is going to look like it's a lot more than the thing that's smaller, okay? Because, you know, for obvious reasons. So the thing is, with chemistry, it works out the same way. What we were saying is that each individual sucrose is a lot bigger than each individual glucose. And so if you want to make the analogy here, think of this like the kidney bean. Think of this like the lentil bean. I hope I spelled that right. Okay, the kidney bean is obviously a lot larger than the lentil bean. This molecule is a lot larger than this molecule, all right? And so just like that example, if you had one individual one of these, it would weigh more than one individual one of these. It would, not only would it weigh more, it would take up more space. If you had a dozen individual of these and a dozen individual of these, a dozen of these would weigh more than a dozen of these. All right, let's take it one step further. If you had 6.02 times 10 to the 23rd of these, it would weigh more than if you had 6.02 times 10 to the 23rd of these guys. Okay, so what I've got here, this is 1 mole of glucose. That's what 6.02 times 10 to the 23rd molecules of glucose looks like. Obviously, it's not exactly 6.02 times 10 to the 23rd, but it's pretty within reason. That's pretty darn close. Okay, the first, I can say that the 6, the O, and the 2 are accurate, but the zeros after that, who knows? But it's not really relevant. Okay, this right here is a mole of sucrose. All right, so that's 1 mole of sucrose, which means in that container there is 6.02 times 10 to the 23rd molecules of sucrose. All right, so I'm going to hold one of these guys next to the other. Does it look like there's the same amount in both of those? It looks like there's twice as much of this guy as there is that, and there is. If you were to put this onto a scale and weigh how much powder you have in each, this one there's going to be more grams of sucrose here than there are grams of glucose here. And why is that? Okay, if you have the same number of molecules in each, but each individual molecule here is a lot larger than each individual molecule there, it would make sense that it would look like there's a lot more of this than that. All right? So let me just give you one more visual on that, is to think about H2O. All right, obviously compared to either of these guys, H2O is really small. All right, whereas that's what 6.02 times 10 to the 23rd molecules of sucrose looks like. That right there in that beaker is what 6.02 times 10 to the 23rd molecules of water looks like. This looks like it's almost nothing compared to this, but these two things have one thing in common with each other. They both have the same number of molecules in there. They just differ in the size of each individual molecule. All right? So, so the next thing that we're going to be moving on to is asking the question, how did I know that that was 6.02 times 10 to the 23rd molecules of sucrose? All right, how do you figure out how to get that many molecules in there? Okay, so what I'm going to be talking about here is, well, I said earlier that in both these are each 1 mole. This is 1 mole of glucose, this is 1 mole of sucrose. And I made the statement that what that means is that there's 6.02 times 10 to the 23rd molecules in each of these, all right? But obviously I didn't count out individual molecules to get those in here. Instead, what I did is I used a scale. I put the beaker on a scale, I zeroed it out, I added exactly a certain number of grams of sucrose here. But how did I figure out how much to do that, how much to add there?